Hello, class. This is section 1.5 again, this time part 2. Continuing where we left off, we just did example 2. So now one-sided limits. One nice way to see that, we kind of talked about it already a little bit, just did not define it as such. But one nice function example that kind of shows it's going down at least a little bit is this Heaviside function. We define it with a capital H to be a piecewise function, 0 if t is less than 0, and 1 if t is greater than or equal to 0. So as t approaches 0 from the left, h of t approaches 0. Likewise, as t approaches 0 from the right, h of t approaches 1, right? And typing that into decimals can unfortunately be a pain when it comes to piecewise functions. But, we could certainly show it going on. Here's the value here of 1. But it's saying that we get a value of 0 if t is less than 0, so we would have an open circle here. And then, actually, let me use a different color just so we could see that a bit nicer. Open circle there. Goes down like this. Likewise, at the value of 0, t, this function is 1, so we have a closed dot here, and it goes off in this direction. So it's a piecewise function. It's kind of broken in that sense. But you could see, if we approach, again, different color for this, let's do purple. If we approach the value of 0 from the left, right? We're approaching the value of 0 if it's from the left. So the limit as t approaches 0 from the left, which is what this negative here means, is from the left, we get a value of 0. Similar to that, if we approach 0 from the right, we get ourselves a value of 1. So the limit as t approaches 0, this is from the right, our function would be 1. And as you can see, these don't match. And they don't have to match. I mean, in some respects, it's better if they match, but for what we're currently doing, it does not matter that it's not matching. So the left-hand limit, as we were just saying, this is where the limit as x approaches a from the left. So that negative aspect on there of f of x is L, while the right-hand limit is where the limit as x approaches a from the right of f of x is equal to L. That just is shown in both of these graphs. So this one here is on the left side. Values of x below a, we approach that value of L for that limit. Likewise, this one here is to the right. Values of x above a as we approach it from that sense. But again, technically they don't have to equal, which is what did not happen before. But we can combine these, right? Since we were talking before about just the limit, not two different sides, we could say that the limit as x approaches a of f of x, the limit as x approaches a of f of x is equal to L if and only if the limit as x approaches a from the left of f of x equals L, and the limit as x approaches a from the right-hand side of f of x is equal to L. Which is why, and let me just go back for one quick second, since these two are different, the overall limit as the value of t here approaches 0, not from either side, since we could see the limits are two different numbers, this limit of h of t, the overall limit, does not exist. Since they're two different numbers, and as we just said in this particular slide here, they have to be the same for this limit to actually make sense and give us a value. So just showing that a little bit here. We have a function g of x being this piecewise function. We want to determine if they exist. Limit as x approaches 2 from the left. So 2 is here from the left. We are approaching where this open circle here is, this value of 3. Likewise, from the right, we are approaching this open circle, which is a value of 2. Excuse me, value of 1. Value of 1. 3 and 1 are not the same, so the overall limit as x approaches 2 of g of x does not exist. I'm just going to abbreviate it. The limit as x approaches 5 from the left. Let me just, actually I'll use a different color. The value of 5. So from the left, we are approaching this number here, which is 2. If we approach the limit as x approaches 5 from the right, also approaches the value of 2. So the overall limit as x approaches 5 of g of x, since the left and the right limits are both 2, is 2, despite that we have a defined value. So we kind of already answered this a few moments ago by having left and right values not being the same, but can the limits not exist? Yes, we've seen it just now with piecewise functions. A limit can fail to exist at a number a if the left and right hand limits are not equal. Likewise, this also happens if we have any oscillations or increasing or decreasing without bound. What does that mean? We'll find out. So example 4, limit as x approaches 0 of sine of pi over x. So again, why I couldn't make a table for it. Before I show the graph, actually, let me actually make the table. Just because if I showed the graph, it'll give the answer. Might as well do it this way first. If we put in a value of, let's say, negative 0.1, and for x, we get ourselves a value here of 0. If we put in a negative 0.01, we also get a value of 0. Likewise, if we put in a value of positive 0.1, we get 0. If we put in positive 0.01, we also get 0. So we're tempted to say that this limit at 0 is, well, 0, right? Since, I mean, the sine of 0 is, well, 0. But, and now this is where the putting it into the graph is important for us to see what's going down with this graph. Let's type in, shall we? Sine of, this is pi divided by x. Ooh, we see a whole bunch of mishmash going on in there, right? It looks almost like a big block because of it. But let us, well, let's increase this. You could see the closer and closer we get to 0, we're not any more defined, unfortunately. And as you can see, it even stops trying to generate the different lines after a while because of just how much it's oscillating back and forth. This is not a value of 0. It oscillates back and forth way too much for it to be a value of 0. So something like that, due to the oscillating nature, this does not exist. Again, why is that? That's because of the oscillation. Due to the oscillation involving that graph. So then example 5, let's find the limit as x approaches 0 of 1 over x squared. if it exists. So with this, let me also, again, it's going to tell you the answer if I put it in immediately. Let's throw in a couple of values. Negative 0.1. This gives us a value of 100. Not large, but nothing too terrible. Negative 0.01 would give us a value of 10,000. That's increasing by a lot. Likewise, if we put in positive 0.1, your scale 100. If we put in positive 0.01 again, we get 10,000. We could see it kind of increasing a lot. Likewise, let me just edit this function just so we could see it. You could see, and I mean, I could zoom out on this so you could see it even better-ish. We approach this value of 0. We approach it, but it's never going to equal 0. We don't have it defined anywhere near 0. It's never going to equal 0, and it increases without bound. So, because of that, this one also does not exist. I should also make note that because both of these increase without bound, despite if x is negative, positive, this one we could also write it using a concept we're about to go over, of this limit being equal to positive infinity. Well, infinity is not a number, but a concept because it increases without bound. Increases without bound. So that's part 2 of this lesson. Be on the lookout for part 3. Thank you.